The next thing we're going to talk about is Charles's Law. Now, Charles's Law is best demonstrated with liquid nitrogen balloons. Now, liquid nitrogen is a substance that boils at minus 196 degrees Celsius, so it's super cold. Now, if we take balloons, we're going to demonstrate here in this video. And we take them, they're room temperature right now, and we take them and we stick them in liquid nitrogen. I want you to see how big they are right now, how they fill the whole container. Now, as time goes on, you can see they're slowly starting to shrink and shrink and shrink until eventually they're nothing. So you can fit all three balloons in there, no problem. They shrink right down due to the decrease in temperature, but as they start to warm up to room temperature water again, they're all of a sudden inflating back to regular size. Now, the rate at which they're going to expand is actually fairly predictable, and it's predicted by Charles's Law. So Charles's Law, what this states is that Charles found that all gases expand by the same ratio as the temperature change. So for each degree increase or decrease in temperature, we can see that the gases expand by a certain fraction, a predictable amount. So if you've got a balloon X at room temperature, for every degree decrease it has, it loses 1 over 273 of its volume. For every degree increase, it increases by 1 over 273 of its volume. It's quite predictable. Now, we can see this ratio of expansion to decrease in size. If we follow it back, we can see it goes back down to 273. Regardless of what gas we're looking at, the x-intercept is always negative 273. Negative 273, we have another word for. This word is known as absolute zero. This is the point that every molecule in the known universe stops moving at. Now, using Charles's findings, Lord Kelvin created a new temperature scale that's more appropriate for chemistry than the Celsius. It's known as the Kelvin scale. The starting point, which is 0 degrees Celsius, or 0 degrees Kelvin, is called absolute zero. It's equivalent to negative 273.15 degrees Celsius. Each Kelvin scale equals a unit in Celsius scale. So, for example, if I wanted to convert 22 degrees Celsius to kelvins, we're going to plug it into our formula here. Temperature in kelvins is equal to temperature in Celsius plus 273. So, temperature Kelvin is 22 plus 273, and that equals to 295 kelvins. On the flip side, if we want to figure out 315 kelvins, what that's equal to in degrees Celsius, we're going to use the same formula. So temperature Kelvin is equal to temperature Celsius plus 273. So 315, temperature Celsius plus 273. And at this point, we can see that this is equal to 42 degrees Celsius. So Charles's Law states that the volume of a fixed mass of gas is directly proportional to its Kelvin temperature when the pressure is kept constant. This holds true for all gases, doesn't matter what type of gas it is. We also have to keep in mind that these temperatures refer to kelvins. Kelvins is what we use in chemistry. So this animation here, this is of a fixed volume of gas at a temperature of 298. Now I'm going to be able to slide it along. And if I pick different temperatures, we can see that my volume of gas is starting to increase. So let's take this and cool it down. This graph is going to start to animate what this looks like. So the temperature decreases, and all of a sudden the pressure of the gas naturally decreases. This is true with our formula we have over here. So if we're looking at two different circumstances for our gas, the initial volume and the initial temperature, or initial volume over the initial temperature, is equal to the final volume over the final temperature. And as we can see from this graph that's animating right here as we speak, we can see that it's proportional. It's predictable. So a birthday balloon So I've got a really neat video here about a tanker truck. Now see what happens is, it's at full size right now, and all of a sudden it just crushes. Now why does it do that? Well, it had a really high temperature on the inside. And what they did with the liquid is they cooled it really rapidly. And when they cooled it, the pressure on the inside automatically just crushed it like a tin can. And it did it quite instantly. So let's apply this. A birthday balloon is filled to a volume of 1.5 liters of helium gas in an air-conditioned room at 294. The balloon is then taken outside on a sunny day and is left to float as a decoration. The volume of the balloon expands to 1.55 liters. Assuming that the pressure and amount of gas remains constant, what is the air temperature outdoors in kelvins? What we're going to do first is list what we know. We know that the initial volume is equal to 1.50 liters. We know the initial temperature is 294 kelvins. We know that the new volume is equal to 1.55 liters. But we're trying to figure out what the temperature is outside. So now we've got this information, we can plug it in to our equation. And our equation is V1 over T1 equals V2 over T2. So 1.50 over 294 is equal to 1.55 over T2. Next thing we're going to do is we're going to do some cross multiplication. So 1.50 T2 is equal to 1.55 times 294. Now we want to have T2 by itself, so we're going to bring that over. So T2 is equal to 1.55 times 294 over 1.50. So now we get out our calculators. So 1.55 times 294 divided by 1.50. So that tells us that our temperature outdoors was equal to 303.8 kelvins, or with correct significant figures, 304 Kelvin.